Assalamu alaikum everyone. I hope all of you are doing great. In this video, we are going to discuss some important inequalities and some limit theorems. The inequalities that I am going to discuss in this lecture are very useful tools that you will find very helpful. Moreover, regarding limit theorems, one limit theorem is central limit theorem that you have already studied. Today, we will discuss law of large numbers. The one is weak law of large numbers and the other one is strong law of large numbers. But before going into the details of law of large numbers, let us discuss some useful tools in probability, which are some inequalities, among which the first one is Markov's inequality. That is defined as probability of random variable x greater than equal to a is less than equal to average of random variable x over a, where this a is a constant. Moreover, this random variable x takes only non-negative values. Another useful inequality is Chebyshev inequality. That is defined as probability of x minus x bar greater than equal to k is less than equal to sigma x square or variance of x divided by k square. Here this k is a constant. Now for this Chebyshev inequality, let's suppose you have a density function whose curve is given as like this, and let's suppose its average is given here, which is x bar, and it has a spread or standard deviation of sigma x. Then let's suppose you are at point x here, then the distance from this x bar to x will be x minus x bar, and you are calculating the probability of a point k. Then in this case you are calculating the probability for which x minus x bar, this distance, is greater than or equal to this k. It means you are interested in this probability, which I am shading with red color. Because you are using here the modulus operator, you are evaluating this area. You can say this x bar plus k, and this point is x bar minus k. Then in the Chebyshev inequality, you are interested in the probability that I am shading with this red color. So what are the main advantage of these inequalities? Why and when we can use them? Let's suppose you do not know anything about the density function or distribution function of your random variable x. Then how can you calculate the probability for this shaded area or for this range? These inequalities can provide you a tool by which you can find the probabilities for these ranges without knowing the density or distribution function of your random variable. Now let us apply these inequalities using an example. Let's suppose we know that the number of items produced in a factory during a week is a random variable x with mean 50, then what can be said about the probability that this week's production will exceed 75? In other words, we are interested to find probability of x greater than 75. As in this example, we don't know anything about the density or distribution of random variable x, so we can use the Markov's inequality to find the probability for x greater than 75. So according to Markov's inequality, it will be equal to x bar over a. Here this a is 75. There a is a positive constant. So we have a is equal to 75. So our mean is 50 and a is 75. This probability will be equal to 2 by 3 or 0.6667. So the probability that the items produced in a factory exceed 75 items is 0.6667. Now let's suppose if the variance of a week production is known to equal 25, then what can be said about the probability that this week's production will be between 40 to 60? In other words, we are interested in this probability. Now let us calculate this probability. So we are interested to calculate this thing x minus 50 less than equal to 10. If you expand it, it will be equal to 40 less than x less than equal to 60. It is simple mathematics. So using Chebyshev inequality, we can express it as 1 minus probability of x minus 50 greater than 10, and it will be equal to, using the Chebyshev inequality, 1 minus, as you know, it is sigma x square over k square. Here our k is equal to 10, then it will be equal to sigma x square over k square, and it will be equal to 1 minus sigma x square is 25, whereas this 10 square is 100, and it will be equal to 1 minus 1 by 4 is equal to 0.75. So production atoms between 40 to 60 has a probability equals 0.75. Now let us try to understand graphically this Chebyshev inequality. Let's suppose we have a density function for this problem looks like this. It is totally hypothetical density function because we don't know what is density function exactly. That's why we are using the Chebyshev inequality. So let's suppose the hypothetical density function looks like this. Then in this case, here you are actually calculating the probability between this range, which is beyond 60 and less than 40, whereas this probability or this thing you are calculating this probability. As you can see, this is 75% area, whereas this thing is 25% area, and the total area is equal to 1 as expected, because we know that the area under the density function is equal to 1. Now come back to the inequalities. Here you may observe that these are inequalities. These inequalities may not provide you the exact result. What does it mean? Let us try to understand it using another example. Let's suppose you have a uniform random variable whose density function looks like this. It is valid from 0 to 10, and if you want to calculate its mean or average, you know that you have already determined these expression. This x bar is equal to a plus b over 2, where this is equal to a and b is equal to 10. Then 0 plus 10 over 2 is equal to 5. So this uniform random variable has an average equals 5. Similarly, you have determined that the variance of uniform random variable equals b minus a whole square divided by 12. So putting these values of a and b, what you will have is 10 minus 0 whole square divided by 12 is equal to 25 by 3, which equals 8.333. So here there is a random variable x which is uniformly distributed and its density function is given here. This uniform random variable has average value of 5 and its variance is 8.333. Now let's suppose you want to calculate the probability which is x minus 5 magnitude greater than equal to 4, then it will be equal to probability of 1 greater than equal to x greater than equal to 9. It means you are interested in this probability. This is 9 and this is 1. You are interested in this area. So from this density function you can calculate the probability. You have to integrate this density function from 0 to 1 as well as from 9 to 10. It means you are integrating this density function whose magnitude is 1 by 10. This is the density function plus 9 to 10. So putting this value of 1 by 10 or value of this density function, it is 1 by 10 0 to 1 dx plus 1 by 10 9 to 10 dx. So it will be equal to 1 by 10 x 0 to 1 plus 1 by 10 x 9 to 10, and it is 1 by 10 into 1 plus 1 by 10 into 1, which is equal to 2 by 10 or 0.2. So this is the actual probability that you have determined using this density function for this range. Now let us try to find the same probability within this range using a Chebyshev inequality. Then what we will have is sigma x square over k square. Here this k is equal to 4 and sigma x square we have determined it is 8.333. Then it will be equal to 8.333 divided by 4 square, and it will be equal to 0.5208. So using the Chebyshev inequality you are getting this answer, whereas using this density function you are getting the probability of 0.2. 0.2 is less than 0.5208. So you get this value using Chebyshev inequality, whereas you get this value using the density function. It is the actual probability that is representing this thing. Whereas you are getting this probability using Chebyshev inequality. Although this probability is correct, but because Chebyshev inequality is an inequality, this is representing an upper bound of the probability for this problem. So the upper bound that Chebyshev's inequality provides does not need to be close to the actual probability. Let me repeat, the upper bound that Chebyshev inequality provides does not need to be close to the actual probability. Now let us do another example to understand the difference in values if we use the Chebyshev inequality or use the direct approach using the density function of random variable x. Let's suppose we have a Gaussian density function which has the average value x and standard deviation or variance is equal to sigma x square, and it is Gaussian. So if we use the Chebyshev inequality, then the probability of x minus x bar magnitude greater than 2 times the sigma x will be equal to sigma x square over k square. We are using Chebyshev inequality first. So here the k is equal to 2 sigma x. From here, so putting the values in this equation, we have sigma x square over 2 sigma x whole square, and it will be equal to sigma x square over 4 sigma x square, and it is equal to 1 by 4 or 0.25. So this is the probability when we use Chebyshev inequality, and we are getting 0.25. Now let's suppose we calculate same probability using the density function of Gaussian random variable fx of x. In this case, this probability of x minus x bar magnitude greater than 2 times the standard deviation sigma x will be equal to probability of x minus x bar over sigma x magnitude greater than 2. I am transferring the standard deviation here. So it can be represented as probability of x minus x bar over sigma x greater than 2 plus probability of minus x bar over sigma x greater than 2. So because we have the magnitude here, we can expand this probability into some of these probabilities. So here we can represent it 1 minus probability of x minus x bar over sigma x greater than 2, whereas this probability can be written as x minus x bar over sigma x less than minus 2. So here make one correction, it is less than equal to 2. Now I can write this probability as 1 minus f of 2.0, because here we have x minus x bar over sigma x. We can evaluate using the table of unit variance and zero mean Gaussian random variable, and here we have f of minus 2.0. So here 1 minus f of 2.0 plus this can be written as 1 minus f of 2.0. This thing is equal to this thing, and it is equal to 2 times 1 minus f of 2.0. And so we can determine the value of this f of 2.0 from the unit variance zero mean Gaussian random variable table, and from this table here you have the value 0.97725. So putting this value here, you have 1 minus 0.97725, and it will be equal to 0.0455. So here, if we use the direct approach to find the probability, to find this probability using the density function of random variable x, which is Gaussian, we get the probability equal 0.0455, which is totally different from this probability, which is greater than 0.0455. So in this case, we get different values if we use Chebyshev inequality and the direct approach using the density function. So we can conclude that Chebyshev's inequality is valid for all distributions or densities of random variable x, but we cannot expect the bound or upper bound on the probability to be very close to the actual probability in most cases. Now come to the law of large numbers. There are two laws of large numbers. One is known as weak law of large numbers, whereas the other is strong law of large numbers. Let us first understand the weak law of large numbers. Let's suppose you have n random variables x1, x2 up to xn, and they are all independent and identically distributed, and they have a common mean. Because they are all identically distributed, they have common mean, which means x1 bar is equal to x2 bar is equal to xn bar is equal to x. Because they have common mean, I am dropping this subscript and writing this x bar, the average of random variable x. Then if you calculate the time average, I am repeating, I am saying time average, which is different from statistical average. If you calculate the time average of these random variables, this will be, I am representing this time average with x hat. It will be x1 plus x2 plus xn divided by the number of random variables, and this x bar is representing statistical average. Then the weak law of large numbers states that the probability of error between time average and statistical average is less than equal to epsilon if the limit n tends to infinity. That means number of random variables is large, then error between this time average and the statistical average is within the range epsilon. It has the probability that tends to 1. This is weak law of large numbers. Whereas for strong law of large numbers, we have same independent and identically distributed random variables which has time average that is represented by xn hat, and we have a statistical average x bar. Then the strong law of large numbers states that the probability of error between time average and statistical average is 0 with limit on n, which is the number of random variables, is large or tends to infinity, then this probability is equal to 1. You can say it is a tighter bound on the error. In the strong law of large numbers, the error between time average and statistical average is equal to 0. If n tends to infinity, then the probability is equal to 1. In this case, this epsilon is equal to 0. Now let us try to understand this concept using an example in which we will take a time average of n samples or random variables and statistical average, and we will see or observe the error between them. Let's suppose you have a noise source and this noise source has a density function fx of x which is exponential, which is representing exponential random variable, and it has an average value of 4, whereas its variance is given as 16. So let's suppose I am drawing a hypothetical waveform. Let's suppose it has this waveform and you sample it. After passing through a sampler, then you get these samples which has magnitudes equal to 0.1, 0.4, 0.9, 1.4, 2.0, 2.8, 3.7, 4.8, 6.4, 9.2 and 12.0. Let's suppose you receive these 11 samples after sampling this random waveform which is exponentially distributed. Then the time average of this n samples or random variables, because this is a random waveform, whenever you sample you get a random value. Because you are receiving a random value, we have these numbers which are actually representing your random variables x1 to xn, as we have seen here. Because this is a random waveform, for each sampling you get random values, and let's suppose these values are given here and you take the time average, which means you are adding all these values and dividing the sum with 11. Because you have 11 samples, what you get is time average. I repeat, this is time average. You get time average is equal to 3.9727. Now if you observe that this x bar is equal to 4, so the error between the time average and the statistical average, it is equal to 3.9727 minus 4.0. This error is equal to 0.273. So you can verify that the weak law of large numbers, in which case this error is 0.0273, and let's suppose we put an upper bound on error which is 0.3 or 0.03, then the probability will always be tends to 1. So regarding strong law of large numbers, we need to extend the number of samples, where in our example we have only 11 samples. If you want to reduce this error, you need to increase the number of samples n, and it must be tends to 0. As long as you increase the number of samples in your time average, this error will keep reducing, and at the end, for the very large number of n, you will get 0 error. Hopefully you have understood all the concepts in this video. In this video, we have discussed Markov's inequality and Chebyshev inequality. We have solved two examples to understand the concepts in Chebyshev and Markov's inequality. We observed that the upper bound that Chebyshev inequality provides does not need to be close to the actual probability. That means if you find the probability using Chebyshev inequality, it will provide you an upper bound on the probability. You apply Chebyshev inequality when you do not know about the density function or nature of the random variable. Whereas if you find the probability using the density function, if you know it, then you will get the actual probability. And these probabilities using the Chebyshev inequality or the direct approach using density function, they may not be equal to each other in most of the cases. Secondly, in the last of this video, we studied law of large numbers and we studied both of its kinds. The one was weak law of large numbers, other was strong law of large numbers. Hopefully you have understood all the concepts. If you have any question, please feel free to contact me or you can comment below. Thank you very much. See you in the next video.